Okay, so in this video, we will first understand what multiplication really means inside the linear layer and let that intuition serve as a motivation to build more efficient algorithms. So what does the linear layer do? It takes these parameters. Now PyTorch defines the linear layer as this: x times w transpose plus b. I'm going to make b 0 in this video for simplicity. I am going to use an example where each data point has 2 dimensions. So input dimension is 2, which corresponds to these in features. And the network has just one neuron, which is also the output neuron. This corresponds to the out features, and I'm going to denote that by this O. So in features is 2 and out features is 1. For simplicity, the batch size is going to be 1. Okay, so the input should have a dimension as usual of n by I, and the weights matrix should have a dimension of O by I. So our input vector could look like something like this. Let me show you here. It could look something like this. By the way, this is not the dimension, but it's like the real values of that vector or input. And the W could look like something like this. This is not the dimension, but these are the real values of the weight vector, which is automatically generated by PyTorch for this single neuron. It is also 2-dimensional. Okay, so when we apply that formula, W times X transpose, will end up with this 4. Now, because we only have one output neuron, this produces one number as the output. But in this video, I will help you understand what is happening geometrically. So let me start by drawing both this X and W. Maybe I can put this here. I can bring this diagram here. Okay. You can see this. All right. So this is X and this is W vector. And this is the coordinate of X drawn from the origin, coordinate of W drawn from the origin. Now, this X is the input vector, and this W really is the neuron's learned direction, its feature detector. So when we compute that X times W, we are essentially asking in geometric language, how much does this X point in the same direction as W? That is the geometric meaning of multiplication in a neural network. So essentially, multiplication is measuring alignment. This means that we can actually compute that dot product X times W using this geometric formula. I'll bring it in here. Okay. We can compute that X times W using this geometric formula, and this is the length of W, this is the length of X, and this is the angle between them. If X points in the same direction as W, this is going to be large, and if X points in opposite direction, let's say here, is going to be large negative. It's going to be a large negative value. You can apply this formula yourself and you will end up with the same result as the algebraic computation. I won't do this in this video. I will leave it as an exercise for you, but when you do, you'll end up with the same result. So that is how a neuron measures alignment. Essentially, each neuron learns a weight vector W that defines the direction in feature space it cares about. When an input aligns with that direction, the neurons fire strongly. So multiplication isn't just arithmetic, it is the neuron detecting something. I will include a Jupyter notebook for different X that you can play with. So for different combination of X and W. Now, let's connect what we have learned with decision boundaries because they are connected. Maybe I can move things around here. Maybe I'll move this formula here and bring this. Okay, so this was X and this is W. So really our vector W determines a decision boundary, which is really a line in 2D and a hyperplane in higher dimensions. And that line is perpendicular to W, which means like the angle between them is 90. And all set of points, let's say X times W, that are equal to 0 will form this boundary, this dash here. And any coordinate that gives a positive result when we multiply it with W will end up in this region here. And any coordinate that gives a negative result when you multiply it with W will fall in this this region. Okay, so the direction of this W defines how the neuron separates the space. And when you have bias, for this example, bias is 0, but when you have it, it helps to shape this boundary, this decision boundary, up and down, which gives the neuron extra flexibility for classification. So learning really is, what learning is about finding a good W so that you will end up with a good decision boundary that accurately classifies our data. And a neural network is a collection of these boundaries detecting different features. Maybe this W could detect, let's say, a particular feature in an image. It could be an image example, and we might have another W. We might have a lot of these Ws. So a neural network is a collection of these Ws that have their own decision boundaries. And you want to find the best set of Ws that have different decision boundaries perfectly placed in, not perfectly, but really accurately placed in different positions in space that accurately classifies the data. Now let's go back to this in features, sorry, this out features, because this is really important. It defines how many neurons we have, how many detectors we have, and each neuron has its own W, its own direction. And having more out features gives the network more ways to recognize patterns. But we can only take advantage of that when we have enough data to train those detectors effectively. Okay, so let's look at how ideas from the brain connect with building more efficient neural networks. For example, quantization. Biological neurons don't use perfect precision. They are noisy. We can mimic that through maybe quantization, like using 8-bit integers instead of 32-bit floats. This reduces memory and speed of inference. And finally, we should maybe ask ourselves these important questions. Since neurons we are really measuring alignment, do we really need full computations? Can alignment be computed with simpler operations? Or maybe could we approximate the dot product more efficiently, sorry. So really these are the kind of questions we can ask ourselves if we want to build more efficient algorithms. All right, thank you for watching. Let me know if you have any question in the comment. Bye bye.